Hey everyone, it's Ken. I just want to give you a few examples of showing the substitution rule for indefinite integrals in action. So first I want to look at an example that's similar to what we've seen before. So suppose we look at maybe cosine of x squared, but this time just times x. I want to show you like how you can handle this, or like why the substitution rule is useful for situations like these. And so right, if this were 2x dx, then you'd know that was f of g of x times g prime of x. You'd know that that's equal to the integral of cosine of y, which is therefore sine of y, and then you plug back in y equals x squared to give you sine of x squared plus c. But say you didn't know that, if you just still focus on the fact that you want your variable to be x squared, so whenever you're doing a substitution, like a change of variable, look for something that's maybe like composed in a function, or like you're taking a square root of it or raising it to some power. That's typically what you're going to want your new variable to be, and so that it'll simplify your integral. And then you get dy equals 2x dx. So there's a little trick you can do. You can rewrite this as 1/2 dy equals x dx. And it kind of a funny little x there, I'll fix that. And this might not seem super mathematical, but what you can really do is you can directly substitute the x dx in here and get cosine of y. And x dx is there going to be 1/2 dy. So I'll put 1/2 dy there, but then you can factor out the constant and bring it out here. And you continue on and you do the integral, and you get 1/2 sine y plus constant of integration, which then following your substitution y equals x squared gives you 1/2 sine of x squared plus c. And if you followed along the previous video, then that was an explanation for why this substitution rule works. Here we're talking about the mechanics of just putting that rule into action. And so why is this definitely giving you the right answer? Some of you may have noticed that another way that you could do this problem is you could say, look, I can rewrite my integrand cosine x squared times x dx. You can rewrite that as 2/2, times x. 1 is equal to 2/2. Show you what I mean. Just 2 divided by 2 times x. Why do you care about doing that? Because now you can just factor out the 1/2. And what you're left with is cosine of x squared times 2x dx. And now this is the integral that you know how to do, straightforwardly from last time. So when you're taking this equation and rewriting it in that form, what you're basically doing is learning how do you split up that derivative in such a way that you actually get the derivative function there on the inside. And so that's why it actually always works for you when you plug it in. So let me show you even another example. So let's say I want to do the indefinite integral of sine of natural log of x, and let's divide by 2x. So you might see where this is going already, or it might just be some funny composition divided by 2x. There's no rhyme or reason. But if you stick with this substitution rule process, we at least recognize here in the parentheses we've got natural log of x. That's our candidate for the new variable. So I'm going to say y equals natural log of x. And then I'm just going to sort of follow my nose. I'm going to say, well, what's dy? dy, that's always going to be the derivative of natural log of x. That's 1/x times dx. And then I can start doing my substitution. So I recognize 1/x dx. So where is that in the problem? This is sine natural log of x over 2 times 1/x dx, if you want to think of it that way. And so when I go ahead and do my direct substitutions, I'm now going to get sine of y, and then divided by 2 and my 1 over x dx. I'll even write out one more step. So this is 1 over x dx. Just making the algebra completely clear. And so now you can see this 1 over x dx. That's what I'm going to replace with dy. So I come over here, and I get sine of y over 2 dy. And now I can integrate that. So you can bring out the 1/2. Integrals are what we call linear, so you can bring out the constant. You're taking integral of sine of y dy, which is now just going to be equal to, well, I have to think about what's the antiderivative of sine. It's going to be negative cosine, so I'm going to get minus 1/2 cosine of y plus a constant of integration. And remember, that's not your final answer. The substitution rule process says, like, you can do this and get this result, but then you have to go back and unsubstitute, right? Replace y with what it's equal to. So you actually come up here and say this is now equal to, this expression now is equal to minus 1/2 of cosine of natural log of x plus some constant of integration. And so that's just a couple examples of how we use this substitution rule to compute any derivatives, at least those any derivatives that involve a change of variable.